The forces of nature are exceedingly strong. In the face of great forces, rigidity is one road to failure. But nature points to a solution. The structure that bends or gives survives. Flexibility is one road to strength. Nature, in her quieter aspects, seems to embody permanence in massive outcroppings of limestone and granite, suggesting a second road to strength. Traditionally, engineers and architects have followed this second road, buying time and strength with weight and cubage. In hydraulic structures, they've employed the same conventional design, building traditionally out of brick, stone, tile, and monolithic concrete, heavy, rigid materials. And until the turn of the century, they had no choice, for no other materials were available to them. Then there came a revolution. It had begun in the blast furnace and the open heart of the steel mill, with the I-beam and the H-beam, the girder and the steel cable, all light, strong, flexible materials. The results were dramatic. Architects and engineers, no longer bound by heavy materials, suddenly set free from traditional methods, created new forms to fulfill new functions, to meet the developing needs of a new era. In light, flexible construction, feats of strength, durability, and economy, to which no masonry, however massive, could ever aspire. Soon the revolution spread to roads and highways. The horseless carriage, a light, flexible metal structure too. At first a product of visionaries, a rich man's toy, destined soon to bring great changes in the land. The revolution took many forms, entered in unforeseen ways into the lives of the people. One new form was corrugated metal, a new flexible material designed for an old function, for culverts, for sewers, for drainage, for use underground. But the voice of tradition was heard. A new material for drainage? Why? Drainage is no new function. Why flexibility, underground of all places? What's needed underground is strength. And it's true. This new material didn't look strong to builders who were used to masonry and concrete. Some builders believed in the new material and bought it. But engineers, by and large, continued to use the drainage materials they knew well. And then, in the early years of the bright new century, the culverts under their roads began to go to pieces at an alarming rate. Engineers and officials began to look under their roads, and what they saw disturbed and perplexed them greatly. These structures had always held up before, and now, apparently the earth had begun to shift, and the whole world wasn't enough support. They couldn't explain it. And then, as they continued their inspections, they noticed something else. Those flimsy metal culverts seemed to be holding up under the very same loads, the very same impacts, the same high fills. Certainly this required an explanation. Over a period of years, the explanation was supplied. A series of studies by engineers in the universities, by railroad engineers, and by public road departments marked the beginning of our theoretical knowledge of drainage structures and the forces that operate underground. For the purposes of their studies, the investigators divided culvert installations into two classes, those in trenches and those under fills, known as projection conditions. They paid greatest attention to the latter, the more common, subjected to greater loads, the major source of trouble through early failure. At the outset, little was known of these crushing forces. Some thought the load forces were wedge-shaped, or larger than the fill above. Some thought they were arched, or less than the fill above. Nobody before had thought of actually measuring fill loads to resolve these conflicting opinions. An early study proved what now seems obvious. The load acts vertically, producing equal pressures under equal columns of fill. But an entirely different effect was discovered when the fill was placed over a model of a rigid pipe section. At this point, with all scales moved back to zero, we start measuring the load. The scales show that the rigid pipe bears more than its due proportion of fill weight. Easily explained. In the deeper side columns, more settlement takes place than in the column on the rigid pipe. Thus, the side columns, in settling, exert a downward friction on the center column. The vertical load on the rigid pipe is equal to the weight of the fill above it, plus some portion of the weight of the side fill exerted through friction. But with a flexible pipe under the same conditions, it was found that the load bearing on it was less than that under the columns of fill at either side. In this case, the deflection of the flexible pipe under load causes the center column to settle more than the outer columns. Accordingly, the shear friction of the soil acts upward on the center column. so that the side columns support part of the weight of the center column of fill. With flexible pipe, the loading therefore is equal to the weight of fill minus the factor of friction. From this, it is apparent that under equal loading conditions, the flexible pipe is subjected to considerably less load. The next question was, how much less? The American Railway Engineering Association was interested in the results of flexibility discovered at Iowa State College and reaffirmed by the University of North Carolina. In 1923, the American Railway Engineering Association made full-scale tests. Pressure cells in pipe under actual fill loads up to 35 feet demonstrated that in deflecting, flexible structures distribute a large part of the load uniformly around the circumference. The vertical load is reduced. The side pressures represent the support contributed to the structure by the surrounding soil. Measurement disclosed that under the loading conditions of the test, vertical pressure was only 54% of the calculated earth pressure. The side pressure was relatively high. By contrast, with rigid pipe, side support was relatively slight, and vertical pressure was 158% of the calculated earth pressure. From this test, two general conclusions may be drawn. Rigid pipe under ordinary projection conditions is subjected to a load greater than the fill load, concentrated at the top and bottom. Flexible pipe, by contrast, carries less than the fill load, and in resisting this load, draws upon the surrounding earth for support, gathering therefrom great strength. The way the rigid and flexible pipes react under load can be summed up by this simple demonstration with a cardboard mailing tube. On the rigid pipe, the pressure is concentrated at top and bottom. But when the pressure is distributed evenly all around, as happens on flexible pipe, that pipe becomes tremendously strong. But how strong is it? The deflection of the pipe under load offers a clue to the answer. As the load increases, the pipe continues to spread horizontally, building up increasing side support or passive pressure until equilibrium is reached. The pipe is designed so that deflection ceases at 5% or less. Inasmuch as the pipe can safely deflect up to 20%, this gives a design factor of safety of 4 or more. The percentage of deflection is a measure of the load being supported by the pipe, and also of the remaining margin of safety. This fact has an important practical application. Because of it, each flexible drainage structure becomes a strength laboratory in the field. The decrease in vertical diameter merely indicates that the pipe is taking ideal advantage of side support and has used only a portion of its available strength. This feature offers an opportunity to increase the strength of the structure by preforming the pipe at the factory to elliptical shape. Riveted corrugated metal pipe may be held in elliptical shape by means of rods or wires installed at the factory. Riveted and nestable pipe, as well as multi-plate pipe, can be held elliptical by vertical timber struts. Such strutting retards the deflection during the backfilling operation. Here we see how the various methods of preforming and strutting can increase the load-carrying capacity of a 60-inch 8-gauge corrugated metal pipe from 25 feet of cover for round pipe, to 50 feet for elliptical pipe, to 65 feet for wire or rod strutted pipe, to 100 feet for timber strutted pipe. The accomplishments of flexible drains and culverts testify to astonishing strength. An 18-foot railway job under a main line. Shallow fill gives little protection against the pounding of some of the heaviest rolling stock in America. No evidence of any deflection. A battery of 16-foot metal culverts designed to support heavy loads of blast furnace slag, crushing impact and live load, still retain their original elliptical shape. An 18-footer, moderate fill, seems to justify the designer's confidence. Twin 66-inch corrugated culverts under 60 or 70 feet of rock fill, ample safety factor. Then the granddaddy of the fill heights, 165 feet over a line of 66-inch corrugated metal pipe. This speaks for itself. For combined dead and live load, look at the spur line that twice a day since 1927 has carried one of the heaviest wheel loads on record. A thermos car charged with molten iron with a total weight of 346 tons. Under the roadbed, a 72-inch culvert. Deflection normal, no signs of distress. Thus, in cases such as this and thousands of others, flexible pipe in all diameters and gauges has proven its strength in use. But while we are interested in resistance to loads as they act on the cross-section of the structure, this virtue is useless unless the conduit as a whole is capable of maintaining its structural integrity underground. To retain its function as a full-length structure, the conduit must also resist the transverse forces caused by general settlement of the soil above it, forces which tend to pull it apart. These same forces are often magnified by local settlement or undermining. In the case of short sectional pipe, fill settlement may cause joint separation. Subsidence of the fill foundation may produce unequal settlement. Short sections are unable to bridge soft spots in the foundation. When end sections are deprived of support, progressive undermining threatens adjacent lengths of pipe and the safety of the roadbed itself. With flexible drainage materials, long sections and positive connections provide uniform strength, resist joint separation. The structure can easily be installed with camber to provide against excessive settlement under high fills, conform to local settlement of the foundation, cantilever when undermining occurs. Service records afford plentiful evidence of beam and joint strength. In cases of undermining, the pipe cantilevers and continues to come to a good end. Economically speaking, a flood may not be a complete washout, since the culvert may often be recovered and replaced. Convincing proof is the case of an outfall sewer, which during installation was whipped out of shape by a sudden squall. After straightening, the entire structure, still watertight, was sunk into place without further incident. In aerial sewers, beam and joint strength and long sections are essential elements of design, equally so in marshy land or swamps, and wherever fluid soil conditions are prevalent or seasonal. Thus, corrugated metal drainage structures respond flexibly to their underground environment, and in flexibility find a better road to strength. We are accustomed to thinking of the topography around us as permanent, yet even in the most massive works of nature, permanence is merely relative. In time, erosive forces pulverize the stone, scour away the soil, and flush the highlands downhill to the plains. Thus, nature points out a second road to failure, by material deterioration. Everything we build, above or below ground, is subject to the same forces of deterioration. And when we modify the landscape closer to the needs of human enterprise and convenience, bridging or diverting or channeling or containing the flow of water, particularly then must we take into account the erosive effects of hydraulic traffic. We may also encounter the added hazard of chemical action. And so of each drainage material, one must ask the second question: will it disintegrate by chemical or hydraulic action before its normal span of structural life? For material durability, glass might be ideal. It's inert chemically, highly resistant to scouring, but too brittle. Special metals and alloys might do nicely, but they're too costly or otherwise unsatisfactory. Somewhere in between are the common ferrous metals, and of these, iron of low carbon content and high purity seems to be the most resistant to corrosion, the most practical structurally, and most feasible economically. Then, to shield the base metal from corrosion, coat it with a protective metal to serve as a sacrificial element in the electrolytic action. If the coating process is well designed and carefully controlled, you get a coating that affords a high degree of corrosion resistance. How long will it last? Valid proof requires not a select handful of cases, but a broad survey of thousands of examples. And since 1920, thousands have been inspected and re-inspected by highway and railway engineers and other competent groups. As a basis for evaluation, an ingenious rating system was evolved, by means of which the remaining useful life of rigid and flexible structures can be stated in percentage terms, from 100% for new to 0. This method is like that used by all insurance companies in setting up their mortality or life expectancy table. By plotting the results of thousands of inspections on a graph with age as one axis and percentage of useful life as the other, you can get a fairly good indication of the probable lifespan of various types of drainage structures. It was found that under normal conditions, corrugated metal structures protected with galvanized coatings have a greater life expectancy than prevalent types of rigid drainage material. Let's look at the record. A twin 24-inch culvert installed in 1907 has survived nearly annual floods. The road has been widened twice without need to replace the culvert. Installed 1912, soon to be retired after 42 years of service. Another veteran under a U.S. highway that's seen the road improved about it more than once since 1915, far surpassed the planned life of the original installation. A large culvert, vintage 1928, carries an important state highway. A 36-inch veteran, dating to 1915, has far outlived the expectations of the county engineer who took an early chance on galvanized metal. A well-preserved specimen of the year 1913. Even the galvanizing has survived the years. As would be expected in any type of pipe, the first signs of disintegration by erosion and corrosion are found around the invert. Distress there may be evident while the balance of the structure is still sound. With hydraulic structures, as with a well-known pneumatic structure, wear is concentrated around a small part of the circumference. For balanced design, the tire employs a heavy tread. Wouldn't the same approach add greatly to the life expectancy of a drainage structure? Why not achieve balanced design in drainage by reinforcing the invert? But how? And with what material? After many years of research in methods and materials, asphalt seemed to offer the greatest promise. Inert, flexible, highly adhesive, but obviously it would have to be a special kind of asphalt, one that would retain flexibility at temperatures below freezing and resist impact without spalling, one that wouldn't flow under the heat of direct summer sunlight. It had to be impervious to air and water, resistant to acids, alkalis, and salts. Moreover, it should be able to withstand the impact of stones and solid debris. Of course, there was no such asphalt until this research produced it, an asphalt specially developed to provide balanced culvert design for severely erosive conditions of use. Now, culverts could be paved where the wear comes. The makers had high hopes for their new product, hopes in which they have not been disappointed. In West Virginia, 400 asphalt-paved invert culverts were rated by engineers from the State University. After about 8 years in use, inspecting engineers forecast they would last twice as long as plain galvanized metal pipes. A reinspection of many of these same culverts when they were 26 years old showed that the original predictions were quite conservative. The pavements in the pipe were still giving protection to the galvanized metal underneath. Here's one, installed 1928. Since then has been carrying acid mine waters. Coating remains excellent. Only small portions of the pavement are missing. Another of the same age, same type of service, paved invert in excellent condition. Another after 24 years of service. No visible evidence of erosion or corrosion. The balanced design of the asphalt paved invert assures the engineer and the builder many added years of trouble-free use. The research scientist and the engineer are agreed that extreme conditions constantly demand more and more durability. But improvements in that line are not easily come by. In time, the search for greater durability narrowed down to asbestos, rot-proof, chemically stable, with a strong fibrous structure. To bond it, why not use the protective metallic coating as a superglue? And once you've spent a few years learning how to coat your sheets that way, then just roll the asbestos against the molten metal coating tightly, so that the fibers become partially embedded in the metallic coating as it solidifies. Then impregnate the outer fibers with a bituminous saturant and give it a double coating of that special asphalt. Then take a sharp implement and try to cut through to shiny metal. It isn't easy. Then bury it. Run through it sanitary sewage and hot corrosive byproducts of a blast furnace for 13 years and find it still in good condition. Pickle it for years in the green waste of a modern industry. The result? You improve the toughness of asbestos bonded and coated pipe. Or bury it under a railroad and run the heaviest and fastest of modern trains over it. In a single run of 159 miles, the Chesapeake and Ohio's cracked trains crossed one metal culvert per speeding minute. The first was installed in 1907. Since then, almost every rigid culvert replaced on this section has been of flexible metal. Not a single failure to date. 50 years of continuous research. Now, with flexible materials in all shapes, gauges, and sizes, with various coatings and pavements, the engineer can design into his drainage structures strength and durability balanced to the conditions of use and the planned service life of the project. These are the essential ingredients for economy. There was a time when most public structures were built for the ages. Labor cost little, there were no stockholders, no boards of estimate, and the taxpayers were not voters. Engineers then could afford to build for the ages, but their works outlived their usefulness. and we call them monuments. Now the taxpayer and the stockholder are represented in the builder's plans. Where utility comes first, we build no 1,000-year structures for 50-year uses. Our criteria of design are strength and durability, and the sum of the two, economy. We buy the service life we need. But in buying, we often think of the price of material at the factory. Of course, a material isn't a drainage structure until it's in the ground, performing its function. Thus, the real first cost is the sum of a series of cost items. First, before you know what to buy, you have to design the structure. It's helpful to employ materials that are factory-made to uniform, close specifications. Lets the engineer bypass tedious, time-consuming stages of basic design. His time's expensive. He saves time when the design is already in the material, included in the first cost. Then there's the cost of transportation. Truckage charges vary with the ton-mile per trip. Rail rates vary with the weight in cubic space, as do water rates. For equivalent diameters, metal has only about 1/10 to 1/4 the weight of sectional rigid pipe. If cubage were no matter, carriers of identical size could easily transport up to 10 times as much metal as rigid pipe. But cubage is a matter, a very important one, easily solved in metal by concentric nesting of different sized pipe, or by stacking of nestable pipe. Then comes laying, lining, and joining. Looks easy, doesn't it? Well, it is relatively easy. Flexible pipe is easy and fast to handle. No danger of breakage. No special equipment. Less time, less labor cost. Easier, too. Much work has been done at the mill, reducing on-the-spot operations. As to making the fill, that can go ahead as soon as the pipe has been laid. As soon as the fill's in, heavy equipment merely helps to compact it. As soon as the fill is compacted, the structure has reached its full strength, and the surfacing job can go ahead. No tie-up of expensive equipment. Less interference with highway and railroad traffic. Midwinter installation with fewer precautions and less cost than with materials requiring heating to prevent freezing. A beveled end provides an efficient outlet at little added cost. In almost every drainage project, flexible materials offer unusual opportunities for economy. An airport to be expanded over a stream. Because of dewatering difficulties, assembly of an entire conduit on the back, a launching of the first pipe, followed by its mate. Thus, a new material has brought in its train a revolution of new techniques and uses. And in every case, flexible metal provides an economical solution. The revolution that began in the blast furnace, the open hearth and the rolling mill, the first won acceptance above ground, and in time ushered in our modern way of life, has over 50 years become an accepted construction material under highways, railways, airfields, and city streets throughout the world. New highways to progress, new roads to economy.